All right, let's begin with a word of prayer for the first time. Dear Heavenly Father, we thank you for this day and the ability for do-overs. Amen. All right, let's see here. Try this again. The first time. Let's see here. I'm trying to think of something interesting, and that's where I went wrong. I mean, let's see here. What did we do? Well, last time we looked at, just plain conformal mapping, right? Like, let's see here. Oh, goodness gracious, my brain broken today. I don't know why I'm trying to do anything. Why am I doing this again? All right, so if I look at U, if I look at V, let me just ask the question. If I look at U of x comma y equals to a constant, what does that look like? Does it look like anything geometrically? I don't know.
Visualize that.
Yeah, I guess. I could take the log of both sides, I suppose, supposing C is positive, but I guess the easier thing to think about, right, is if you take a grid, right, in the xy plane, like this, and then you map it by the exponential function, then like what happens to it, So if we look at, a typical horizontal line would look like what? Like here. That would be z equals to what? Like at, well, let me just say it would be equal to like t plus ib, or iy naught for a fixed y. Right, so if I look at f of such a z, I get the exponential of t plus iy naught, which is what? Exponential of t times the exponential of iy naught. So if, and I'm just being boring. This is for 0 less than or equal to t less than or equal to 1. I'm just looking at a little unit grid. Okay, so like y naught is some particular y between 0 and 1, just for the sake of specificity. And if you look at that, this is the image of that horizontal line under the exponential. What's it look like? Well, this is a particular direction over here, right? What's what's this? This is just some unimodular complex number. It's a unit vector in the direction. Well, it has angle y naught actually. So that basically, and exponential does what? It goes from 0 out to e. So poor planning on my part. All right, so this, e to the, so there's some angle y naught, right? And it goes from 1 out to e. Let's see here, something like that. So this gets mapped to this ray, right? That horizontal line gets mapped to this ray. And then if you look at the vertical line, what does it get mapped to? So that would be, z equal to, say x naught, right, plus it. And so f of z would be equal to e to the x naught, e to the it. So this is a fixed radius, a fixed polar radius in the image, and that sweeps from angle 0 to angle 1. So 1 radian is about 57 degrees, something like that. So basically you're looking at e to the x naught, which would be, man, it's bigger than 1. It's somewhere. Let's see here. So that would be, this is not x anymore. Over here we have the uv plane, right? The others. So I'm just saying we sweep from angle 0, basically, to angle, so something like that. And if you do this, for all those, you'll eventually create what?
What are they called?
Remember the name.
I don't either. Not concentric.
It's some sort of sector, right?
Yeah.
So that's what the exponential function is. Complex exponential function takes a square grid like that, and it blows it out to this sort of sector. Let's see here. So if I wanted to go all the way around, how would I get like an annulus here, like continuing this? If I want to just, thought experiment, if I want to do like this. How should I make my grid bigger to make that happen?
You just can keep extending it upward.
Yeah, right.
Yeah,
Take this up
just
to,
needs to be larger.
right, just keep going, take this up to 2 pi, right? And then that will loop it all the way around, right?
Yeah.
Okay, so cool thing, just to show you how the conformal mapping works. So let's look at that annulus. So suppose you want to find a solution to Laplace's, what we can do is we can find a solution to Laplace's equation on the annulus. I'll show you guys how to do that. So this inner radius is 1, right? And the outer radius happens to be E in my current, thing. So let's suppose we want a voltage of, I don't know, what do you guys want in the middle? We'll make it 7. There.
So
Yeah.
variable.
This is 7. We'll make it 11 out here. All right. So suppose you want phi. Did we call it little phi or capital phi last time? I've forgotten our lingo.
Big phi.
What's that?
Big phi, capital phi.
Capital phi. Okay. So little phi is the one we pull back. Is that our language?
Oh, sorry.
Was it little phi of xy?
Little phi was the composition of
Okay, that's what
big phi of.
Very good. So we're finding the big phi to start with. So, all right. So you study complex enough, all right, to know that we can use. So the log of u plus iv is equal to the natural log of the square root of u squared plus v squared. Of course, that's the modulus. And then plus I times the arg of u plus iv. So the point here is that this is the real component of complex function. More to the point, holomorphic. All right. In other words, it's complex differentiable. So the fact that that's the real component to a complex differential function tells me that this is actually a solution to Laplace's equation in the UV plane. But that gives me the idea to search for solutions that can fit here. Basically, I just do something kind of like similar. What I'm going to look for is, how's it go? I want something like a natural log of the absolute value of w plus b. That's going to be the real part of what we call big phi, all right? So what a and b would I choose here? In other words, so like I want 7 equal to a times the natural log of the, so, oh, this is actually really nice, look at that. This is like way nice. Check that out.
Nice.
It's almost like I made this up on purpose as I prepared for class with the tons of time I have to do that this semester. So 7 equals to b. And this tells me that 11 plus a, oh, excuse me, you get to the point. What's a equal to? So that's 1, right? So a plus b, it's 11. That makes a 4. So what I figured out is that if I do 4 natural log of w plus 7, that works as the real component of phi. Let's see here. So I don't know if we really needed the whole complex function to do the thing, but I want to figure it out. I'm curious. So what's I think so. Our phi would be what? It would be like 4 times the log. Right, 4 times the log of w, right? And I guess just plus 7, if you do that, this has the real part of that. Right, there's also a IR piece that we don't really care much about. Right. So the cool thing is, if you look at little phi equals to f of big phi, right? Oh, other way around, right? I'm sorry. Oopsie. If you look at little phi equal to big phi of f, so little phi of z will equal to big phi of f of z. This is the way we steal solutions over here back to solutions over here. Like this, by the way, just to emphasize. This right here, this solves Laplace's equation on this annulus with an inner voltage of 7 and an outer voltage of 11. So it solves this equation, phi uu plus phi vv equals to 0, with phi 7 out here and phi 11 out there. So that'd be how the voltage, the voltage distribution in the absence of charge in the annulus. Let's see here. Now, this, where did these, I'm trying to remember, how did, right, I mean, technically, there is a little trouble for the argument. Like, you can't make the argument go all the way around. Like, the argument will solve Laplace's equation on like a slit annulus. You can't go all the way around because there's a discontinuity in the arg. Like, if I try to go full circle with arg, I get run into the 0 goes to 2 pi. I get the discontinuity. The discontinuous function is not twice differentiable, or once differentiable. I mean, discontinuous functions are hard to differentiate. But anyways, for a slit, for the slit annulus, and you can, pick an angle that you want, whatever slice, whatever slit annulus you like. The imaginary component of this thing, which is 4 times that, will be a solution to Laplace's equation. But anyway, it does not have the 7 and 11 boundary conditions, right? That's not the case, but it actually is, of course, it's actually constant on rays for what it's worth. But okay, so what's this? So this would be phi of, well, f of z is what? Well, f of z is e to the x cosine y plus I e to the x sine y, right? So in other words, my u is e to the x cosine y, and my v is e to the x sine y. And then I would plug that in to the real component of the complex function. Now, I explained last time why that composition has to be a complex differential function. Basically, there's a chain rule in complex analysis that says that this would be a complex function. I don't really care about this. I just want to look at the real part of it. This differentiates. Little phi prime would be big phi prime of f of z times f prime of z. So it's complex differentiable. Consequently, its component functions are solution to Laplace's equation. I don't care about the whole complex thing. I'm really looking for the real solution, so I just look at the real part of that. All right. So the real part of that is just, what is it? It's 4 times the natural log. And we can, the square root, right? You can rewrite this as 1/2 of u squared plus, so let's do that. Instead of 4, we'll write 2. And then u squared, so that would be e to the 2x cosine squared y plus, oh, this is dumb. This is dumb. E to the 2x sine squared y, this is really dumb. Sine squared y, we're not going to like this when we get done with it. This is not as powerful. Last time we found some very powerful demonstrations of this technique. This is not going to do that. This is about to become really, really dumb. And yeah, Yawnsville. Let's see here. Oh, plus 7, yeah. So if you tilt your head and squint, that's sine squared plus cosine squared, which is 1. And then e log of e to the 2x. This is a really convoluted way of writing 4x plus 7. Now does this solve? This solves little phi xx plus little phi yy equals to 0 on the unit interval 0 to 1 across the 2 pi interval 0 to 2 pi, right? And you know what? It also has phi of 0 comma y equal to 7, right? And it has phi of 1 comma y equal to 11. So that's kind of the cool thing here, is I can use some color coding. This inner boundary here, right, where we had phi equals to 7, maps to x equals 0. So that is getting transported back to this thing right here. And the outer boundary, this guy, right, that's tracking over to here. And the discontinuity from here to here is manifest, right? Well, I guess it's, well, maybe it's not. I mean, I don't know. Shut up about that. Sorry, this is not that exciting an example. I mean, but there you go. That's the solution to Laplace's equation that we pulled back from the annulus. We managed to find something far more interesting last time. So, but this is basically the idea: is to solve Laplace's equation on some standard shape in the target space, and then recognize the shape we're mapping to as the image under a complex function of the domain we're interested in. There's kind of a lot of moving pieces here. Now I want to shift gears and just show you guys the hyperbolic calculus, right? So, because we really want to generalize this method to.
So the good thing was that the theorem says that any equation that satisfies Laplace's equation, you undergo that on a complex, like a complex function, will again is guaranteed to solve Laplace's equation once more.
Right.
The
key is that if big phi is complex differentiable, then if I take big phi and I compose it with another complex differentiable function, the composite is complex differentiable, and consequently that composite gives me a solution as it happens. On the
we did that today.
Oh yeah, that was just the rewording of the theorem you gave us last time, I think. Yeah.
Oh, did you do that today? And
Yeah.
No. I mean,
Well, for complex, that was a property of the analytic function, which is
yeah.
complex differential.
yeah, again, just to it's worthwhile to state the general idea. So here's the concept. So here we have, XY space, and then over here you have the UV space, right? And then, so there's some sort of standard blah, and you have a big phi, which satisfies particular boundary conditions in some sort of standard shape. Let me not call this blah, let me call this, I just need a name for it. We call it G last time, was it?
G or D?
Was it G?
Yeah, G.
And then basically the point is back over here.
5:00 p.m.
It's not really like that, but you have some D, right? And so if you can get F, where F of D is equal to G, then big phi composed with little f is little phi, and phi prime is really just big phi prime. Well, I guess I got to put some point dependence here. Big phi prime of z is equal to essentially d big phi df dz. So the point is, if that, if this is another, and you can denote this p prime of f of z if you like, to be more explicit. The point is, if you can solve, if you find the cool thing is if you find a solution to Laplace's equation on this that matches certain boundary conditions, and then you can see that as the image under f of some complex differential mapping, then the boundaries map to the boundaries. Like, again, the last time we had better examples, but for example, let's see here. So I could look at the slit complex plane f of z equal to the square root of z, the principal square root. So how is the principal square root defined? You take the modulus of z, and you square root ordinary garden variety square root. Let me write that as, this is dangerous notation, but here I really do mean the plain old real, this is not a set of values, this is the plain old garden variety square root function, okay? Be careful, because in Churchill, the 1/2 often means the set of values. So for a complex exponent, if you talk about the set, the set of values would be plus or minus this. Square root comes with two things. Anyway, and then you do e to the I arg of z over 2. Now the reason that that's like a pretty, if you call this thing w, you can easily prove that w squared is equal to z. It's one of two solutions to that equation. If you try to solve the equation w squared equals to z, there are two solutions. The principal argument and, well, there's many solutions. But here's one way to write it. The other way is like minus this. But you could, well, anyway, you can play games with the argument. You can choose other arguments. And, all right. But what does this one do? Look at what happens to the angles. So you start, the slit complex plane, because this is where the principal argument is not continuous. It jumps from pi on the top to minus pi on the bottom, right? That's how it works. So what does this thing do to the slit complex plane, as it's called? What's it map to? Over here in the W plane, or the UV plane, if you like. You can kind of see here the e to the, if you say W is equal to modulus of W times e to the I beta, using beta for the angle in the UV plane, what does beta range over? In other words, beta is equal to arg c over 2, right? By definition, minus pi less than arg z less than or equal to pi, right? But let's just say less than pi because I want a differentiable function, including the equality gives it discontinuity. I don't know, anyway, I'm not going to fuss about that here. So, divide by 2, what do you got? Right, so where does it map to in the UV plane? Not the whole plane, but the half plane, right? So that slit complex plane maps to the half plane. Like that. Right?
Oh, that was similar to what we did the other day.
Mm-hmm.
Yes.
We did it backwards, didn't we?
Yeah, we looked at z squared. What we did was we took the half plane and we squared it to get the whole plane, right? Now I'm playing a slightly different game. So let's see here, and like where does the it's something like this, right? You've got this part of it mapping up here, right? And this lower edge kind of, I should really probably draw these dotted. They're not actually mapped to, right? But if they were, they'd be here, right? So we could solve I guess we could solve Ploss's equation over here in some kind of weird way if we wanted to. Like, we could put, I'll just be lazy, I'll put pi over 2 volts up here, and I'll put minus pi over 2 volts down here. So we'll use phi, again, phi of w equals to, log w again, actually, but this time not quite what we want, right? Because this is log absolute value w plus I arg w. And arg w is great and all, but it's not, so if I want to how should you say minus I log W, right? Would be minus I natural log W plus arg W, right? So it's fairly easy to see, let me call this not phi, but it's, I don't know, what do you want to call this? G, there. So this is what I'm looking for, in the sense that here's a complex function. It's minus I times log W. Log W we know to be complex differentiable from our larger study of complex variables, which we haven't done in here, right? And there's the
From fundamentals of things we
there's there's the real component, right? So that's the solution to the Laplace's equation, and by the definition of argument, that's pi over 2 on the orange and minus pi over 2 on the blue, and so now we can track that back to a solution on the slit complex plane, which will have a discontinuity. It will approach, if I understand right, it'll approach pi over 2 on the top here and minus pi over 2 on the bottom, if I did this right. So it's, well, I don't know what it's going to, I don't know, I'm kind of curious what this does. I actually don't know. I feel like I'm violating the rules of the method. What happens here? So, phi, right? Phi of z equals to, I'm supposed to do what? Big phi of f of z, but what is f of, ow, what is, Alright, I'm tired of this example. I'd have to figure out the Cartesian form of this thing, you know? It's a 2, not a z, so it's not that bad, but shnikes. Well, if I'm willing to tell you what, I'm going to be lazier. If I, oh, that's not, oh man, oh, why'd I do this? I mean, the modulus is easy. That's the square root of x squared plus y squared, big deal. Fine, that's that part, you know. It's the arg z that's a hassle, because, you know, okay, so if I'm in quadrants 1 and 2, then I have a nice formula without much qualification, right? It's like, well, let's just say it's cosine theta over 2 plus I sine theta over 2, okay? We could write it that way. Just let arg, let's express it that way. Arg of z equals the theta, okay?
To the 1/2, does that need to be factored into that, or the modulus
that's
to the
that's
1?
this right here. That's the modulus of
Okay.
z. Oh, to the 1/2.
Yeah, isn't the modulus?
Oh, you're right.
should
You're
be
right.
the
Right.
fourth, I think, right?
Oh, thank you.
Yeah.
You are correct, sir. That is supposed to be the 1/4. Thank you. That's important. So then I have to feed that, you know. I put that in here, right? And but I don't want phi. I want the not phi, but the real part of this, right? That was our agreement. We're just going to look at the real part, just to be lazy or whatever. And so, oh, how awful is that? So that's the argument, right? That's the argument of that.
Let's calculate it.
It's actually useful to write it that way, right? So that's actually just theta over 2. Yeah. That makes sense. Theta over 2 is this. I mean, theta over 2, which by the way means inverse tangent of y over x, or possibly shifted depending where you are. Right? It's the angle function, which you can define in terms of x, y, in terms of right triangle trigonometry. I mean, it's a pain, but you can do it. The angle function divided by 2 is a solution to Laplace's equation here that goes to pi over 2 up here in minus pi over 2 down there if you define it in terms of selecting an angle between minus pi and pi as per the usual restrictions. So there you go, it works again. But again, this is not nearly as interesting an example as... I am just a wellspring of uninteresting examples today, I'm sorry. I mean... Like, I have a gift today for creating examples which are so simple that they're confusing. And that's unfortunate. All right, hyperbolic calculus is what I want to do. Let's get the hyperbolic calculus. What is hyperbolic calculus, right? But this concept is what we want to generalize to hyperbolic calculus,
Right.
all right? All right, so... First of all, what is hyperbolic numbers?
Gosh.
Non-negative.
So I'll say H is R direct sum JR. So what this is A plus BJ such that J squared is equal to 1. And that's kind of it. So there is a notion of conjugate here. If I say Z equals to X plus JY, then Z bar is X minus JY. All right? And, but the product of Z and Z bar is X plus JY times X minus JY, all right? Which is equal to what? It's equal to X squared minus JXY plus JXY minus J squared Y squared. So these guys cancel as usual, and you're left with X squared minus Y squared. So this is not nice, in the sense that, that's not a length function, right? It's not going to be the square of the length, but it still has significance. I mean, like, there's still algebra going on here. If you look at the product of Z, if you look at ZW conjugate, you can prove it's still Z conjugate times W conjugate. That's a straightforward exercise.
That was on my test.
Should I? But yeah, but here I'm. J squared is not minus 1, so but it is the same reason on your test. Yeah.
Right. Different, yeah.
Yeah. So. So let's see here. If I try to solve Z times W equals to 1, in other words, I try to find, what condition on. So let's say Z is, X plus IY given, all right, plus JY rather. And I try to solve this equation.
Quick question: why are we calling these hyperbolic numbers when they're really just like complex numbers?
They're not though. J squared is 1.
Oh, no,
I'm about to show you a convincing reason that they're not complex numbers. Although there are analogies. Much like the many analogies between Cosh and Cinch.
Oh yeah, because in complex Z, Z bar is X squared plus Y squared.
Yes,
Yes.
yes.
Sorry.
Which is beautiful.
Right. So, if I try to solve this, and let's say X plus, and I'm not sure this is the best way to do this. I should build a little bit more machinery perhaps before we attack this problem, but I'll just attack it now. What equations do you have to solve? You got yourself, AX plus BY equals to 1, and you got yourself AB plus YA, or AY, x times, oh, sorry, bx. Ay equal to 0, right? I guess you could look at this as A, B, B, A times, x, y equal to 1, 0, right? That's not what I want, though. I want it the other way around. Because x and y are given. I'm trying to find a and b, all right? So to solve for ab, what do you get? Flip the x and the x. It's hard to notice. So that gives me 1 over x squared minus y squared. That's ax minus by. This is minus ay plus bx. In other words, we get a plus bj equals to ax minus by plus j times bx minus ay over x squared minus y squared. I think I did something wrong. Just a second here.
Oh, 1, 0 for the.
Yeah, that's. It's like, yeah, I know something's very wrong here because I shouldn't have x's and y's in here. Well, I just made it way harder than I needed to. Sorry about that. Thank you. This is x and minus y, right? Yeah. So we're supposed to have x minus jy over x squared minus y squared. Hey, check that out. What's that? Can you recognize what that is?
Oh, is it the.
Z conjugate. So it's just 1 over z.
So that's like the equivalent of multiple. Are they conjugate?
So that still works here. Now I could have been not done the linear algebra here. We could have just done it this way, right? Z bar equals to x squared minus y squared, right? So z times z bar over x squared minus y squared equals to 1. So therefore the multiplicative inverse of z, when it exists, is z bar over x squared minus y squared, right? There's the argument, sans linear algebra. So, it's not complex numbers. Why? Complex numbers, the multiplicative inverse exists whenever the complex number is non-zero. Complex numbers form a field. Here, we get into all sorts of trouble when y is equal to plus or minus x. Right? So the invertible hyperbolic numbers are those which don't lie on the plus or minus y equals x lines. There are zero divisors on the lines y equals plus or minus x. You know what zero divisor is?
Not off the top of my head. No.
So, for example, 1 plus j times 1 minus j. This is not 0, that's not 0. Multiply them. You get 0. Zero divisor. Product of two things, 0, even though neither of those things are 0.
That's weird.
It's easier to find examples in modular arithmetic. For example, Z6,
No.
2 times 3,
0.
0. Yeah, neither 2 or 3 or 0. So that's some of the rudiments of hyperbolic numbers. They got zero divisors. Now, I study the calculus of functions over hyperbolic numbers. So that calculus is built over the real calculus on the plane. So you have like limits, and real differentiability, just like you talk about in complex analysis. You wouldn't talk about in complex analysis, but in a world where we fit complex analysis into a larger story, we would talk about how complex analysis is a special case of real differentiation on the plane. All right. Limits of functions of two variables. I'm still going to calculate limits. My notion of distance is just Euclidean distance. All right. So like, you know, I don't try to do something hinky and like use this to define some kind of pseudo distance or anything like that. It's not at all the direction we go. We just plain old Euclidean distance. All right, so if you look at oh goodness. I'm trying to think of how to what to skip here. There's so many things to say. So ultimately, I want to study functions, all right, from some subset of the hyperbolics to the hyperbolics again, something like that, all right? So really, what we're looking at is a function which is some subset of R, going from R2 to R2 again, I mean from a perspective of real calculus. All right, so this is a differentiable function if it's, you know, so to say that f is differentiable is to say the limit as h goes to 0 of f of p plus h minus f of p minus the differential at p of f acting on h over the norm of h is equal to 0. So this is what it means for f differentiable at p. Now here, this dp is called the differential. This is a linear transformation from R2 to R2, okay? And the standard matrix of this differential is the Jacobian matrix of f at p, which by the way looks like partial f partial x, partial f partial y. Now typically we use the UV notation, so that's like ux, vx, uy, vy in terms of the components of the Jacobian matrix. So to say f is differentiable at a point means the Frechet quotient goes to 0, which is to say the differential exists and is linear, all right? If the function is, if all of that is true, and if you have, it turns out conversely, if you have these partial derivatives existing and they're continuous, then it follows that the function is differentiable, all right? Now hyperbolic, to say f is hyperbolic differentiable, f, you know, as above, is h differentiable if at p. If f is real differentiable at p, in other words, you got all this, all right? You got the Frechet derivative exists, all right? And there's another condition. And the differential at p of f, all right, acting on v times w is equal to dpf acting on v times w for all v and w in the hyperbolic plane. So here, this is using the h multiplication on R2, which we're saying R2 is the hyperbolic numbers, okay? So like, the identification that's being made is that this two-dimensional vector, AB, is equal to A plus BJ. So this is just like what we do in complex, where we trade sometimes. Sometimes we trade, a complex number for a two-dimensional vector. Here we trade a hyperbolic number for a two-dimensional vector. To be explicit, the correspondence is 1 is equal to E1, and J is equal to E2, where E2 and J are the the standard one. This you know what this is, right? 1 0 0 1, right? You guys know. Okay, so this is a linear transformation. DPF linear transformation, right? So the standard matrix. How do you get standard matrix? Well, you get DPF E1, DPF E2, right? To get the standard matrix, you feed the linear transformation the first standard basis element, then the second standard basis element. That gives you the columns of the linear transformation. We know this, right? But on the flip side, the differential, all right, if you feed it a unit vector, it becomes the directional derivative in that unit vector direction. So this is the directional derivative of f in the E1 direction. That is exactly partial f partial x. This is exactly partial f partial y. So I'm explaining to you why this was the case actually now. So this is partial f partial x, partial f partial y. All right, so here's the thing. This condition down here is mission critical right here. This is the right H linearity of the differential. Check out what that says. dPf of v, right, is equal to dPf of 1 times v, right? 1 is a hyperbolic number. So by that property, this is dPf of 1 times v. So this says that the differential is fixed by whatever it does to the identity. Whatever happens at 1's completely controls the other columns. And so if you look at this dPf of like j, right, that will be equal to dPf of 1 times j. By the same token. So if I have, dPf of 1 equals to, say, a plus bj, then what's dPf of 2, of j rather? Well, it's a plus bj, right, times j, which is what? That's aj plus b, or if you like, b plus aj. Put that together, what does it say the Jacobian matrix looks like? It says this guy up here, right, is a, b, because that's a plus bj, and then the second column is ba. That's a necessary pattern that has to happen for an h differentiable function. So the real and j imaginary, I don't know what the name is. It's not really imaginary, but whatever you want to call it, the other component, you can call it imaginary, but like the first and second components are not, they're not unlinked. They have to be linked by this pattern. So, on the other hand, of course, this is equal to this, right? So this gives you the CR equations ux equals to vy and vx equals to uy. So these are the hyperbolic Cauchy-Riemann equations. there is a sort of Laplace equation here. Is it, Jonathan, are you in complex right now, or no? Okay. So the thing we went through last time is if like the usual CR equations are ux equals to vy, and uy equals to minus vx, right? So if you put these together, you get uxy equal to vyy, but we also get uxy equals to minus vxx. So therefore vxx plus vyy equal to 0, and likewise uxx plus, you can work this out. I mean, I haven't shown that, the second one. But these are Laplace equations, right? So like a complex differentiable function, the real and imaginary components, the u and the v, separately solve Laplace's equation. A hyperbolic differentiable function, something else. We have these equations, right? So when we do this same kind of, exploiting the commutativity of the partial derivatives calculation, what happens? So we have ux equal to vy, and we have uy equal to vx. So this says uxy equals to vxx. This tells me that uxy equals to vyy. So therefore vxx equals to vyy. And likewise. So, and likewise you get the same thing for u. So it turns out we have uxx minus vyy equals to 0, and vxx minus vyy equals to 0. So any hyperbolic differentiable function automatically has solutions of these equations. Now the question is, what we want to try to explore is like, can we find a hyperbolic differentiable function that solves some interesting boundary conditions of some sort or another? I don't know. Isn't it funny that the same matrix came up in our derivation of the inverse? That also happens in complex if you try it, except instead of getting AB, BA, you get AB minus BA. Or minus B up here, I forget, I don't know. Alright, so now we gotta use our imagination. This is completely unexplored territory for me, guys. I'm not sure what I want to do. I mean, so trying to think. I think I don't remember. I mean, I know I can construct an exponential function. I know like square functions. I don't have much experience with the square root function here. Trying to think of how we define a log function. Okay, so like e to the z, I can tell you would be e to the x plus jy here, and that will be e to the x, e to the jy, and that will work out to e to the x cos y